Hello all, welcome to JustQuant. In our previous video, we had a look at understanding the basics of calculating remainders. In this video, we'll see few of the remainder theorems which may help us in calculating remainders faster. Let me first consider the Fermat's little theorem. As per this theorem, if n is a prime number and m is a number that is prime to n, then the remainder of m to the power of n minus 1 when divided by n is 1. That is, to calculate the remainder of 15 to the power of 26 when divided by 13, here we see that the divisor 13 is a prime number. So as per the Fermat's little theorem, 15 to the power of 12 by 13 gives us a remainder 1. So let's use this to calculate the remainder of 15 to the power of 26 when divided by 13. I'll write 15 to the power of 26 as 15 to the power of 12 whole square into 15 square by 13. As we have seen from the Fermat's little theorem, 15 to the power of 12 when divided by 13 gives us a remainder 1. So this becomes 1 square into 15 when divided by 13 gives us a remainder 2. So this becomes 2 square divided by 13. So 1 square into 2 square, which is 4, when divided by 13 gives us a remainder 4. Right? So whenever we have a divisor which is a prime number, we can make use of the Fermat's little theorem to calculate its remainder. Okay, fine. Let's now try to understand the Euler's theorem. But before we look into the Euler's theorem, we need to understand the Euler's totient function. The Euler's totient function gives us the number of positive integers that are less than or equal to n and prime to n by the formula phi of n equal to n into 1 minus 1 by a into 1 minus 1 by b into 1 minus 1 by c, where the phi of n is the Euler's totient function. N is a natural number which is written in the form a to the power of p into b to the power of q into c to the power of r and so on. Here a, b and c and so on are prime factors of n, and p, q, r are the positive integers. Let's consider an example. The number of positive integers less than or equal to 33 and prime to 33 is given by phi of 33. Okay, so the 33 can be written as 11 into 3. So phi of 33 becomes 33 into 1 minus 1 by 11 into 1 minus 1 by 3, which gives us 20. So that is, the number of positive integers less than or equal to 33 and prime to 33 is 20. Okay. So let's consider another simple example to calculate the number of positive integers less than or equal to less than 9 and prime to 9, which is given by the Euler's totient function phi of 9. 9 can be written as 3 square. So phi of 9 becomes 9 into 1 minus 1 by 3, which is 6. Hence the number of positive integers less than 9 and prime to 9 are 6. Okay. So with this understanding of Euler's totient function, let's now try to understand the Euler's theorem. Okay, so if we have a number in the form m to the power of some positive integer x by n, here if n is relatively prime to m, that is, if m and n have a highest common factor of 1, then m to the power of phi of n divided by n gives 1 as the remainder. Here phi of n is the Euler's Totient function of n. That is, as per the Euler's theorem, remainder of m to the power of phi of n by n gives 1, where m and n are coprimes, right? That is, if we were to calculate the remainder of 2 to the power of 63 by 99, here both 2 and 99 are coprime to each other, so we can apply Euler's theorem. So first we calculate phi of 99. So 99 is written as 11 into 3 square. So phi of 99 becomes 99 into 1 minus 1 by 11 into 1 minus 1 by 3, right? So this gives us 60, right? So as per the Euler's theorem, 2 to the power of phi of 99 when divided by 99 gives us a remainder 1. That is, 2 to the power of 60 when divided by 99 gives us a remainder 1, right? So I'll write 2 to the power of 63 by 99 as 2 to the power of 60 by 99 into 2 to the power of 3. We know that 2 to the power of 60 when divided by 99 gives us a remainder 1. Hence, the remainder is 8. So instead of writing 2 to the power of 63 as 2 to the power of 60 into 2 to the power of 3, we can divide the exponent 63 by phi of 99, which gives us a remainder 3. This 3 becomes a new exponent. That is, now 2 to the power of 63 becomes 2 to the power of 3 by 99, which gives us a remainder 8. So if we have a number in the form m to the power of x by n, here we first identify if m and n are coprime. If m and n are coprime, then we calculate phi of n, after which we calculate the remainder by dividing the power of m by phi of n. The remainder obtained becomes the new power of m. In this case 3 becomes, in case of 2 to the power of 63 by 99, 163 is divided by phi of 99, the remainder obtained 3 becomes a new power, from which we calculate our remainder, right? So here we considered m and n to be coprimes. So when we have m and n to be coprimes, we can directly apply Euler's theorem. But what if m and n are not coprimes, that is, they have a factor in common? Let's try to calculate the remainder of 3 to the power of 45 when divided by 45. In this case, both 3 and 45 are not coprimes. So what we do is, we'll write 3 to the power of 45 as 3 square into 3 to the power of 43 and 9 into 5. So the common factor in the numerator and the denominator is 9. So we take out this common factor both from the numerator and denominator and write the new dividend and divisor as 3 to the power of 43 by 5. I'll just make a note of the common factor here. Okay, now both 3 and 5 are coprimes, so I can apply Euler's theorem. So first I'll calculate phi of 5, which is 4, and now divide 43 by 4, which gives us a remainder 3. We divide the exponent 43 by 4, which gives us a remainder 3. So our 3 to the power of 43 by 5 now becomes 3 to the power of 3 by 5, which gives us a remainder 2. right? So now that we have this remainder, we multiply this with our common factor 9 to get our actual remainder. So 18 forms the remainder of 3 to the power of 45 by 45. So what we do here is we see if the m and n, that is 3 and 45, are not coprimes. So we try to identify the common factor, which comes to be 9. So once we have the common factor, we divide the numerator and denominator by common factor, and then we apply our Euler's theorem to get a remainder. The remainder obtained is then multiplied by the common factor to get the actual remainder. Let's now try to calculate the remainder of 32 to the power of 32 to the power of 32 when divided by 9. Here we see that both 32 and 9 are coprimes. So I can apply Euler's theorem and calculate phi of 9, which gives me 6. Okay, so now divide the exponent 32 to the power 32 by 6. Okay, so 32 when divided by 6 gives us remainder 2, so this can be written as 2 to the power 32 by 6. We see that both 2 and 6 are not coprimes, so I'll take for the common factor from the numerator and denominator, which is 2. So this becomes 2 to the power of 31 by 3. Okay, so I'll just make a note of common factor here, which is 2. Now 2 and 3 are coprimes. I can write this as minus 1 whole to the power of 31 by 3, since 2 gives us a remainder minus 1 when division by 3, which gives us a remainder minus 1, which is nothing but 3 minus 1 equal to 2, right? Based on a concept of negative reminders, which we discussed in a previous video. Okay, so this gives us a remainder 2. Now multiplying this remainder with our common factor 2, we get 4 to be the remainder of 32 to the power 32 when divided by 6. Okay, so now that we have the remainder of 32 to the power of 32, our problem simplifies to 32 to the power of 4 by 9, which is 5 to the power of 4 by 9, since 32 gives us a remainder 5. Okay, this is nothing but this gives us a remainder 4. So in this video we looked into the Euler's theorem and the Fermat's little theorem, and we tried to solve some problems based on them. In my future videos I'll try to cover few more theorems on remainders. For now, I hope this is clear. Thanks a lot.